Hello and welcome to Programming Like It's 1979. Today we're going to be looking at the programming/synthesizer game, The Signal State. We're going to play maybe 5 or 6 levels of this just to give you an idea of the flavor. I don't want to spoil the entire game for you, but you'll see what it's about. I call it a programming/synthesizer game because the plot, as you can see us clicking through here, is about living in a post-apocalyptic society where you have to recreate electronics and recreate electronic logic. But the components that you're actually using to do so are largely crypto synthesizer components made that you're connecting via patch cables. You're configuring them and using patch cables to make them work again. So we're at this farm, we have a little bit of plot, we're introduced to some people, and they chose an interesting way to frame this story, which is that for each level, you begin the level, and you have a dialogue with the people you're talking to. And generally, they've done a good job of letting you choose how much you care about the plot. You can reply to the dialogue by asking a lot of questions, as in here, why am I here? Or you can generally just jump to, yeah, I get it, get me straight to the puzzles. So I'll click through with the questions for this one, where Miriam is going to explain a bit about the game, but then for the additional puzzles, I'm just going to say, yeah, give me the puzzle. I did play through the entire game as of a couple of months ago while this was in early access. They've changed a few things since then. The biggest or most significant change is that they've added downloadable puzzles similar to TIS 100 or some of the Zachtronics games. Other users are now making puzzles and you can download them and play them, and you can make your own, which is kind of nice. So we're going to go to our first puzzle. We're going to see a bunch of tutorial prompts explaining that we need to rewire these circuits to make the machines work. So for this one here, we are just going to be essentially wiring an input to an output. We're taking our source and connecting it to the split, and then we're going to take our now split signals and connecting them to the output. The wires tend to be random colors if you leave the game at its default, or you can specify colors for wires. We can also adjust the speed here so this goes a little faster. And when you're done, you get a test which compares your stats to all of the people in the world. So we can see here that my number of modules used and cables used were all the same, but my cable length was too long. And so, although it's not immediately obvious, you can pick any of these things up and move them around. Let's go ahead and make our cable lengths as reasonably short as we think we can. And now we're doing much better. We could also compare ourselves to our various friends. And now we can go on to something that will still be a tutorial, but maybe a little more involved. After each level, you're brought back to the level select, and in this case, we're just going to choose the next level and move on. We got a little more plot. And we're going to be fixing a generator. Begin the game. So in this case, we're building a very small amplifier, essentially. We're going to take in one input, and we're going to triple its intensity. So we have 2 modules here. We have our split module, which is going to take in one signal to that input, and you can output it up to 4 times the same signal. And our sum module, can add up to 4 values and put them out here. I love that all the modules have a little Japanese written on them, which tells you maybe a little bit about how they imagine this world working. And so we want to triple the intensity here, and so we're just going to add this value to itself 3 times. I'm going to use green as my this value is done. I'm going to use yellow, I think, as my this is the unchanged value from one of the inputs. You could hear in the background essentially playing the tone that you're generating. So this really is synthesizer logic going on here, even though it's not strictly a music game. There's a deep nexus between synthesizer games and programming games. There's actually quite a few of them on Steam. And at this point, I'm going to be choosing the yeah, get me to the puzzles answers for anything we encounter. And if you want to explore the plot, if you end up getting the signal state, you can explore it yourself. Am I getting the hang of it? Yeah, I am. We're going to make a circuit breaker. The game was in early access for quite a while. It is on Steam for $19.99, and there is a free demo, so you could actually try it yourself. So now we have this catalog down here. We can start adding things into the rack. We can start rearranging them. They want me to delete this. You can pull them off. We have controls that we can adjust this way with the mouse, or we can just type a value in here. This is our I/O. This is our essentially blue is what's expected. If we hit play now, we'll see a red signal there indicating that that's a bug, essentially, where we have not yet solved the problem. So what is our problem here? We want to send signal +5 to out 1. Well, we have this bias module, which will increase the signal by 5, but we're going to need to send the signal to 2 outputs. So let's go ahead and send it to our splitter. That's going to go there, and that's going to go there, and then out 2 receives source 1 signal with its intensity half. Well, let's go back to our module catalog. We've got this one module that we have not used yet, which is an attenuator. So let's go ahead and lock these things. Feed this to the attenuator. We're going to say we want 50%, right? That should be half. Oops. Probably better to use... Oh, the attenuator is already on there. Well, we can delete it. And send this to out 2. I think I can change the color of that. There we go. Let's see how it looks. And that's the circuit breaker level. So the game starts out, as many of these games do, at a very easy level of difficulty. This is one of the games that I've played this year that I would characterize as a brain burner. It's so hard to choose the right level of difficulty for these puzzle games, because if they're too easy, then they're boring. If they're too hard, then they're impossible. This game really nailed it. There are a few levels, not all of them, but a few levels in the middle of the game that I would characterize as true brain burners, and I banged my head against them for quite a while. And they have that nature where if a puzzle is too difficult, and it's obviously too difficult, you just walk away from it. You say, well, I don't know multivariate differential equations. I'm not even going to bother. These puzzles all had the nature of sounding like things that should be easy to do with all the tools you have at your disposal. We don't have many tools right now, but as we go through the game, more and more of these modules are going to be added. Things like pick the maximum signal, pick the minimum signal. They sound easy, And you find yourself having to be extremely careful, extremely precise. And that was a very brain-burnery experience, and I liked it. So, farmhouse lights. Out 1 is source 1 and 2 summed together. Out 2 is source 2 subtracted from source 1. So this is something the game does a lot. We have 2 objectives here, out 1 and out 2, and one of the objectives is super easy, and one of them is trickier. So we know that we need both source 1 and source 2 in both of these outputs, so we're going to need to split each of those signals. So let's put source 1 there, and we'll put source 2 there. I don't like that color. Let's do that one. I want yellowish, not yellow, not brown. Okay, source 1 and source 2 sum together. Well, we have a sum module, right? So we're going to take source 1 there and source 2 there, and then that is the output for source 1, or out 1. And we can check this, and we can see that on out 1 we've got our yellow line, which is good. And on out 2 we still have not solved, which makes sense because we haven't connected anything there. So how do we subtract 2 from 1? Well, we do not have a subtract module. The only things we have are, other than our oscilloscope and our notepad, you know what, let's connect the oscilloscope just for fun. See what that looks like. Very nice. Okay. So what are we going to do? Well, the other things we have is we have bias, which is a constant offset, and we have attenuation, which right away we see the word invert, so that's probably going to be our answer, but it's also the only component left that might do something interesting. So we know that source 2 is getting subtracted from source 1. So let's go ahead and invert it to 100%. That should be a negative value. And then we will take its output and put it there. Oops. Just going to move all these over. I like minimizing the space. I don't know why. And then we're going to take source 1 here. Put it there, and then our output goes here. And somehow I lost an output. I think that's correct. All right, and there's our farmhouse lights sorted. All right, let's go on to the next level, which is another tutorial level, introducing a new component called the VCA. Voltage-controlled amplifiers. So we can see we have some signals. Out 1 receives a specified percentage of source 1's signal. So we're going to grab a VCA, put it right there. Source 1 is the input. Source 2 is going to control how much of the input reaches the output. Connect the output of the VCA to there. And that's how this works. Let's pause it so we can see, for example, here the input is 55, the control value is 20, our output is 11. 11 is 20% of 55. Next, we're going to wire up the barn lights. They have variable intensity controls. Well, whenever we hear variable intensity, we start thinking about that VCA component that was just introduced. We can have breakpoints. So if we want to check a specific value, we can have the run pause on that time step. I don't think I need breakpoints for this. Send source 1 to out 1, but with its input intensity boosted by 50%. And send source 1 to out 2 but with its intensity boosted by a percentage specified by source 2. Right, so clearly source 1 is going to need to be split since we're doing two different things with it. Let's do this first one first. Intensity boosted by 50%. I think that means we can just take the attenuator, choose 50%, have a sum, right? Then that 50% is going to go there along with our original value. And then that goes to there. Let's test that. Yeah, so our out 1 looks good. Our out 2, of course, is not hooked up yet. Send source 1 to out 2, but with its intensity boosted by a percentage specified by source 2. So logically, this is going to be very similar, only instead of boosting by a static 50%, we're going to boost by a variable percentage. So source 1 is our input, source 2 is our control value, and then we're also going to need to add that value to our variable boosted value, and that goes to out 2, right? We'll move these over just to minimize the wire distance. Probably not as efficient as it could be. That's okay. And that looks correct. Let's set a breakpoint. See, it broke. English, good. I feel like this might be a good place to stop. Let me look at one more. So now they're going to start introducing binary signals. All right, source 2 is a binary signal. When it is at 100 volts, send source 1 to out 1, otherwise send 0 volts to out 1. VCAs, and we have a note here telling us that VCAs can be used as gates. If the CV input only ever receives 100 or 0, then the output signal will always be either 0 volts or the original input signal. Well, that makes sense. So let's take a look here. So we know that source 2 is going to be 0 or 100. In fact, we can inspect the values here, and we see that it's always 0 or 100. So source 2 is going to be our signal, and source 1 is our input to the VCA, and then that's our output. They are going to introduce actual logic gates rather than making us use the VCA in this way. I think they're just showing how it could work as a gate. Essentially, in this case, as an AND gate. Let's do one more. So, source 2 and 3 are binary signals. When they are both at 100 volts, send source 1 to out 1, otherwise send 0 to out 1. So we do not have an AND gate, but we do have a sum, right? So we want this to be when both of these are at 100. So what I'm going to do here is kind of crappy, but I think it'll work. We're going to bias our signals to -100. I believe signals can go higher than 100. I hope they can. Let's find out. Let's see. We're going to step forward here. Nope, 100 plus 100 is 100. So that's a bit of a gut punch. I was hoping to just do some math here and get that answer. Let's see. We can actually use a VCA for this, because if both of these are digital signals, or 100 or 0, then only when these are both 100 will this be emitting 100. Then that becomes the control signal for that. This goes here. Change the color of that. And then this is our output. I think that will work. Let's take a look. Yes. We've done some binary logic using analog signals. And isn't that what synthesizers are really all about? Well, I think I've gone through some of the easy puzzles here, and I really don't want to spoil the game for you. So this is where I'm going to call it. If you have more questions about the signal state, please ask them down below in the comments. As I said before, it's $19.99 on Steam, and there is a free demo. I like the game. I think it's a lot of fun. This has been Programming Like It's 1979. Thanks for watching.